No.
Similar.
Yeah, very similar.
This Giovanni with the wig on.
Oh, jolly. How was it?
It was fun. It was so funny. They never had grilled cheese before. Have you had grilled cheese?
Yes,
It was really like elaborate grilled cheese for the first
okay.
time. It had a lot of stuff. Usually it's just
Yeah. They had it on the cheese.
a lot. I probably wouldn't. But they liked it.
Yeah, also jolly.
Oh, yeah, I should have seen you. So fun. We're gonna do one.
And
One.
hopefully.
Potato.
Yeah.
You all ready?
Yeah.
Do you need the chat up at all for Zoom? Or?
I think there's gonna be another TA who's gonna be on Zoom, so I think hopefully we should be able to.
Okay, I mean, I'll bring it up here just like it's right here, so you should be able to see like.
So I can screen share on Zoom, right? I mean, because I think they're not gonna be able to.
Yeah, no, it should be screen sharing right now. I just checked it.
Oh, okay, got it.
So. So yeah, we should be good.
And rientra with the tourist visa with any information that's possible. You've been there. You've been on the top. Yeah, I turned into a savage when they put me inside the. I turned into a monkey. They put me inside the. It was a lion. I become a different person. Just, you give me the ocean, I become like fish.
What? You just like go in the water.
Yeah, yeah, basically, we love being in the nature. That kind of nature. They told me that I'm to respect them because they grow the planting. Yeah, and we use the color. South America. Yeah, sorry, I put it south, but it's right. For me, there's no central. Like, you usually only have like. Yeah. No, but it's just have to be. Because yesterday night I did the hallucination for them.
Oh, you did it.
Yeah, it's really easy to do.
I'm optimistic about it. I enjoyed it, but I tested it.
And it's then we have a jiu-jitsu that code is useless. I consume the solution and you can just throw it away. This one makes you anyway. So I was like, I really need to do it. Can I start to get it? Stuff. Like, okay. Have fun. How are you doing? Okay. Kind of long. It took me some time to understand dinosaur dogs. And I still have to test it if my understanding is correct. That is Friday night. Okay.
Plans to work.
I don't know, all of my plans seem really busy this weekend. Exams and assignments.
I don't know, I'm gonna go check.
Using hand looks of the tree. If I don't finish it, I'm gonna just go to it. And just go to the max. Yeah, I get it.
Hi, can everyone hear me? Good? Okay. We'll start in another 2 minutes. Okay, so hi guys. Today's recitation is going to be about classification, more specifically for homework 2 part 2. And we're going to walk you through the starter code as well to help you get started with the assignment. So my name is Prakriti, and with me today is Paul from the Kigali campus on Zoom. And we're going to be the moderators for today's recitation. So let's get started. Okay, so our objective for today's recitation is to provide you with a basic understanding of the classification task and also to narrow this down with relation to the assignment, which is homework 2 part 2. And we're also going to take you through the different types of convolutions that you're going to encounter during the assignment, and we're going to describe the data set that you're going to be using, share some basic tips to improve your model performance, and then we're going to run through the homework objective as well as the starter notebook to help you get started. Okay, so let's talk about the classification problem. So as we all know, most applications leverage classification tasks. Oh, oops, I think I might be muted on Zoom. Okay, so as we all know, most applications leverage classification models to perform specific classification tasks. So for example, we have email applications which classify our emails as spam or not spam. We have service providers who provide sentiment analysis on a lot of customer reviews to identify positive as well as negative reviews. And we also have image recognition and verification tasks that are often performed by our devices, like for example, face unlock. So all these applications can essentially be posed as classification problems. So if you guys have read the write-up, you probably know that we have 2 tasks for homework 2 part 2, which is the classification task as well as the verification task. So this recitation is going to focus on classification, while the next recitation is going to be talking about verification. So essentially, classification is a supervised learning method which learns a model that predicts a class of the given input data. So in this same way, the homework 2 task is face classification, which essentially means we're going to determine who it is in a given image. So you guys are going to be training a model which receives an input image, and you're going to output the class that that image belongs to, which is its label. So we have 2 classes or 2 categories of classification, binary and multi-class. So when we just have 2 classes that we're dealing with, we're going to be dealing with binary classification, but more than 2 classes, it's going to be multi-class classification. So in this homework, you guys are going to be dealing with multi-class classification since you have 7,000 fixed classes, that is 7,000 unique individuals in the data set. So when given an image, your model has to assign it to one of these 7,000 predefined set of classes. So before we continue, before we continue, it's important to discuss the difference between closed set and open set tasks and how this relates to the classification task. So in a closed set task, your test samples must come from one of the classes predefined in your training set, which means that while testing, you are guaranteed to see a category that you have seen before in the training set. However, in open set tasks, you have test data that has samples in categories which are not defined in your training set. So your model will be shown images from a category which it has never seen before. And so naturally, in a closed set problem, we're going to learn decision boundaries that will divide our feature space into k number of parts, whereas in open set tasks, you're just going to learn tight decision boundaries around the k known classes that you have seen before. So as you guys would have guessed, classification is a closed set task since we have a fixed number of classes, which means that all the images in the test set must be from one of the classes predefined in the training set, whereas a verification is an open set task where some of the images in the test data set are not present during training. And more of this is going to be, oh, yep, go ahead.
Sorry, yeah, I know I'm really far away.
Yeah,
So
go
for open set, like, can you only predict the labels that you already knew during training?
Right. So the kind of task that we're going to be doing here is where we have like sort of k known classes that we have seen during training, and then we have like some x number of unknown classes that are present during our testing phase. And we essentially have to say, okay, if we take an image from one of these unknown classes, what is the closest class that we can map it to? And that is essentially our verification problem. Whereas in classification, it's less of a how close are these two images, and more what class exactly does this image belong to? Yeah. So move to the next slide. Right, so now we're going to talk about how open set and closed set works based on our classification task. So as you guys can see in this image, we have our training set, which consists of k classes, or rather k unique images, one image per class. And then in the closed set, we have test samples that contain only images which come from one of the categories in our training set. So essentially, we're going to feed the image into the label predictor, and it's going to output a label or an ID, which identifies it to be part of one of the classes that we have seen before while training. However, we see in our open set task, we have identities that do not appear in our training set. And so it essentially extracts features from an image and compares it with features from some other images in a gallery that we have seen before, which would be our k known classes, to see if it's present in that gallery. And that way it's going to be able to output the class that is closest to classes that it has seen before in the training set. Okay, so the homework 2 problem that we're going to be talking about today is a classification problem, a fixed set of classes, and it's a closed set task, as we have talked before. However, you should know that the exact images in your training set are not guaranteed to be in the test samples as well. Simply that the classes that you have seen before will be present in your test set. Since the classification model, however, that we're training is shift invariant, this should not be a problem. So we're now going to be talking about the general training pipeline for the classification model that you're going to be training. So as you see here, we have an input image. And after that, we pass it through a convolutional neural network to extract features which are mapped to a feature space to create the feature embeddings that you see there, or the face embeddings. After which, this face embedding will be passed into a linear layer, also called a projection layer, that will project this onto the fixed number of classes or categories. And then these are the n-class probability logits that you're going to get, after which you can pass it into a softmax, which will just normalize it between 0 and 1 to give you a vector of probabilities. And then afterwards, we can apply cross-entropy loss, which is the standard loss function for multi-class classification. And for regularization, we can use things like label smoothing and weight decay, which we will talk about later. Okay. So as we've discussed earlier, we need to extract features from the input image and create important embedded features which are separable to get a good classifier. And we can use cross-entropy loss to learn a good model which minimizes the loss. The output from the linear layers that we then pass our feature embedding to will be logits, which are unnormalized, and we pass it through a softmax. However, you guys don't need to implement the softmax, as the PyTorch implementation of cross-entropy already incorporates the softmax function. So you don't need to worry about implementing this separately. You simply need to get the feature embeddings and pass it through a linear layer, after which you can use cross-entropy loss. So finally, So we have different convolutional network, neural network architectures, which can be used for feature extraction. And we go into this in detail in the write-up. So we have EfficientNet, ResNet, ConvNext, and other CNNs. So you guys are expected to review the papers for some of these architectures, which we have linked, and implement them from scratch. So you can't use any pre-built models. And yes, there are libraries which have implemented these, but we would want you to code them from scratch to understand the working principles, and also so you understand how to tune hyperparameters appropriately to get good feature embeddings. So now I'm going to hand it over to Paul, who's going to move from slide 12. Yeah.
Thanks, Prakriti. I want to confirm that you guys can hear me.
Yeah.
Oh, okay. Yeah, so one thing we'd like to talk about, we would like to discuss also in this recitation is the working principles of the convolutional neural network and how they are applied to images for feature extraction. So we would discuss two basic types of the convolution, which is the conventional convolution and also the depth-wise convolution. Then we'll basically see why depth-wise convolutions are better than the conventional convolution. So we'll be starting with the conventional convolutions. So this has already been discussed in class. We have an input image. Here, the input image has multiple channels. And then in the slide here, we have 3 filters, each having their own layers. And then each filter convolves with the input image to provide output convolved maps, which are then collapsed to produce the output channel. Next slide. So ideally, your number of filters will be equal to the number of output channels, and each filter will have a number of layers, which is equal to the number of input channels. So you perform a convolution with each layer of a filter and the corresponding input channel, and after which you have performed this. After which you have performed this, you have convolved maps for each input filter and a layer for each input and a layer of the filter, and then that convolved maps is then collapsed by either summing it by summing it to produce the output channels. Next slide. So if we have like n input channels and we want to produce m output channels, we will need like m filters, each having n layers and each layer having a k by k dimension. And when we calculate this, we will also get the number of parameters which will be required, to do this convolution. So that's basically how the conventional convolution works, and I'm sure most people are familiar with this. So up next, we talk about the depth-wise convolutions. So here there are these are actually better than the conventional convolutions. So in depth-wise convolution, it's like unlike the normal conventional convolution, it occurs in 2 stages. So in the first stage is the filtering stage. The first stage is the filtering stage, and what basically happens is that we have filters without layers. Can you go to the next slide? Yeah, so we have in the first stage we have like filters without layers, but the number of filters we have is equal to the number of input channels. So for any input channel, we have like a corresponding filter, and note that all these filters they are different. So we apply convolution once with each input channel and a filter, and each filter can be a size of k by k. So basically like a 2D filter. And then so for each convolution, we produce an intermediary output channels. We call it intermediary because it's not the output channel, since we said there are 2 stages. So this is just the first stage. So we produce intermediary output channels, and therefore we expect the number of these output channels to be equal to the number of the input channels, since we are just using 1 filter per input channel. Next slide. So after producing these output channels, we then go to the second stage of the operation, which is known as the combining stage or the point-wise convolution stage. Yeah, in this stage, this is just similar to the conventional convolution, just that the filters here are just have a size of 1 by 1. So in this stage, we have a number of filters, which is equal to the number of desired output channels. And now each filter will now have a number of layers, which is equal to the intermediary output channel. But however, each layer of each of these filters is just a size of 1 by 1. So that's why it is pointwise. So it's just a filter of 1 by 1, which is basically like a 1D filter. So when we perform convolutions with each of these filter and the intermediary output channels, this will now produce the final output channel, just like the conventional convolutions. So similarly, you can calculate the number of parameters by accounting for the first stage and the second stage. So and when you calculate this, you see the formula. We will have this formula as described in the slides. So now we try to compare the number of parameters required when using the conventional convolution versus when using the depth-wise convolution. So to do this, we use like very simple example. Here you have an input image with 3 channels and a size of 8 by 8. And so for these, so if we're given this kind of input image, for the regular convolution, you will need a filter of 5 by 5. Let's assume that, okay, we are using a filter of kernel width 5. So we have a three layer filter, which has a size of 5 by 5. That's for the regular convolution. But for the depth-wise convolution, we will be having, first of all, the first stage, which is the filtering stage, which is just going to be a single filter, which is 3 filters, each of them 5 by 5, which is same as the input channels, right? And then the combining stage, we just need a pointwise filter, like the 1 by 1, but 3 channels, since we have 3 output intermediary channels after the first stage. And when you now desire like an output channel of 256, and say we also assume that we have a kernel width of 5, you will calculating the parameters for the regular convolution, we see that we will have like 3 channels, each of them 5 by 5, so that they can convolve independently. And since we need 256 output channels, that means we need 256 of such filters. So when you do that calculation, you see this will be the output parameter, the total parameter rather. So, but when compared to the depth-wise convolution, let's look at the first stage. The first stage during that's the filtering stage. So you just need 3. So there are 3 input channels. So you will need 3 filters. Each of them will be a size of 5 by 5, and that will produce this output, these total parameters. For the combining, you will need 256 because that's the desired output channels of a pointwise filter. That's 3 channels, but 1 by 1. And when you just compare the 2 parameters, you see that the one for depth-wise convolution is more, it has lesser number of filters than the one for the regular convolution. I think about 3 times less filters, right? You see that this depth-wise convolution is more efficient. So if you want to train your model faster, you can subscribe to like depth-wise convolution, and we have different architectures which already implement like this depth-wise convolution, just such as the MobileNet and ConvNext. But the ResNet still use the regular convention, like the normal conventional convolution. Next slide. Next one, another thing I want to discuss is like some basic tips in tackling the homework. So first we discussed batch normalization, and I believe this is not new to everyone, to anyone. Like we have done this in class. And also we have implemented this in homework 1 part 1. And so I will expect everyone to be familiar with this concept. So we basically normalize each feature or layer of each batch of the training sample to avoid like internal covariate shift. You can read the paper to get more understanding. One thing batch normalization helps us to do is it helps our model to train faster by allowing us to use higher learning rates. So it gives us flexibility in terms of using different kind of learning rates. And however, but there are some drawbacks to using batch normalization, which is based on the number of samples you have in your batch. So if you have like low compute resource, then we have smaller batches, and this would affect the mean and standard deviation of each of the batches. And then they're causing us to have like poor results. And therefore, an alternative to this is to use layer normalization, which basically also does the same normalization technique, but instead of normalizing in the direction of the batches, we are normalizing in the direction of the channels or across the features. So one advantage of using layer norm normalization or layer norm is that it's not constrained by the number of batches, right? And it computes same mean and standard deviation during training and test. So you can save the values from training and use that during testing. So if you have like an MLP, for instance, like a multi-layer network, so the layer norm will normalize the features, will normalize the across the neurons or across the layers rather than in batches. So I will encourage you to try both out, both techniques in your ablations and determine which one works best for you. And there are also other normalization techniques that you can explore, such as the group normalization or the instance normalization. But however, we believe that layer normalization and batch normalization is enough or sufficient for this homework. Next slide. So label smoothing. So we'll talk about label smoothing. Is also another good regularization technique, which is performed on the label of the training data set. So why do we need label smoothing, right? So oftentimes deep learning models tend to overfit or they become like overconfident in a classification task, especially when you have like a lot of classes. So overconfidence is in the sense of like predicting extremely high probabilities for a particular class, and getting such prediction wrong will cause the gradient loss to explode. So therefore, we will need like to use some form of smoothing techniques to smoothen our ground truth, that's like our labels. And this will allow some form of uncertainty across the other classes, right? And also prevent like the model from being overconfident and being overconfident in a single class, which will like negatively affect the overall performance of the model. So label smoothing just generally like helps you to your model to be more robust and generalize more. So you can find label smoothing. You don't need to implement it. It has already been implemented in PyTorch. When you're applying your cross entropy, it has an argument for label smoothing. So you can set the factor. Yeah. So here we want to just give you like a kind of an understanding of how label smoothing works. So here we have the general equation for label smoothing, and we'll use this example to make things clearer. So assuming like we have like 3 classes, and the output logic vector from the fully connected layer is given as Z, which is ABC, and then we have our true label, which is 1 hot encoded. So if you have no label smoothing on the ground truth labels, like if you perform no smoothing of the true labels, our softmax distribution of Z will be quite different from the true labels, and this will naturally make our model to enforce A and B to be so much larger, right, and decrease. So it makes A so much larger than B and C. But what we want to do is to make the distribution of our ground truth as close as possible to the softmax of our logic vectors, right? And this will aid our gradient descent to perform better and prevent it from being like overconfidence in one particular class. So using label smoothing, we soften the ground truth using smoothing factor of 0.1. So in this case, we are using alpha, which is the label smoothing factor here, at 0.1. So note like this alpha is not like it's a constant, it's like an hyperparameter as well, which you can tune, right, to provide better results. So here you can tune this, and given that k is the number of classes, we can then use this formula to smoothen our ground truth, right? Which is the 1 hot was previously 1 hot encoded. You can then smoothen it to produce YLS. So the teacher said, why do we need label smoothing? Okay, like I said, we need label smoothing to prevent our model from being overconfident. And when it's in overconfidence in one, it makes the gradient descent harder to work. Like, so it explodes the gradient descent loss, because when it's trying to make to enforce only a particular class, is trying to create uncertainty, is not creating any doubts for other classes. It's then enforcing just a singular class, and then it makes one of the classes have a very high probability compared to the rest of the class. So that's why we need label smoothing. So and this is So when you do label smoothing, it is better because your ground truths are now smoothed. They are not like 100. So your gradient descent is better, right? And then you have a better model. So I definitely would want you to test out label smoothing because during our ablations at CES, we found out that label smoothing helps to improve or increase the accuracy of your models. Yeah, so it's definitely something you want to try out in your own ablations. So another useful technique we'll talk about is the drop block. So we all know dropouts in fully connected networks, but this has not been very useful in convolution neural networks. Instead, we patronize drop block because the studies have shown that this works better for as a regularizer for CNN. So it also behaves like dropouts where neurons are dropped, but in this case, neurons are not randomly dropped because in dropouts we drop neurons randomly, but here we drop contiguous sections or like contiguous neurons, like neurons together in a particular place. So in a particular section, we drop the whole neuron in that area, so not random. So and why is this the case? Let's imagine like we were giving like an image, which is an image of a dog, and these pixels have been extracted using the CNN. So if we consider the shaded regions in your figure B as the activation units. So if this is your activation unit and you randomly drop those units, you see that the other units very close to them still retain some semantic information about the dog. So therefore, the model is still able to deduce or get the semantic information you are trying to hide, right? But if you map out an area and drop the whole block in that area, it will probably remove like very important semantic information about the dog. Maybe it removes the legs of the dog or the head of the dog, and this will enforce other neurons, right, to learn important attributes that will make the classifier a good one. So PyTorch also has an implementation for drop block. You can check the link below. To implement drop block, you basically pick like a random pixel and the 2D block is drawn around that pixel. So every neuron or every unit within that 2D block is being dropped. And this is very good. This is a very good regularization technique for CNNs. So we believe that like with these tips are very useful. You should definitely try them out during your applications in your homework 2 part 2. And should expect good results. So for the low cutoff, you can do without them, but to get to the very high cutoff, this technique, these tips, you should try to implement them. Yeah.
Okay, so now we're gonna, can everyone still hear me? Okay, so now we're going to move on to talking about homework 2 part 2. And you guys probably already know a lot of this. We're just going to go over it once more. And there's also going to be a boot camp tomorrow, the 25th. So make sure to attend that to get an early start on the homework. So this homework's objective is going to be to recognize or verify faces in images, and this is going to be solved using a convolutional neural network. So why would we want to use a CNN? Well, this is a pattern recognition problem that requires position invariance because in typical pictures of faces, the face is very rarely perfectly centered, as different pictures of the same person are most likely going to have the face shifted by varying amounts. So whatever classifier we're using is going to have to recognize the face regardless of this indeterminacy of position. And that's where position invariant models, or CNNs, come into the picture. So CNNs derive representations or embeddings of input images that are expected to be invariant to the precise positions of the patterns within these images. And these embeddings can then be classified by downstream classifiers like a softmax layer or an MLP, which are appended into your network after your convolutional layers. So in our classification task, we're going to attempt to identify the person in a picture, which is a closed set problem, as we talked about before, where the subjects in the test set or the classes have been seen in the training set, although the precise pictures will not be in the training set. So in order for us to achieve high accuracy, the only real constraint that we have is that the embeddings of all the subjects in our entire data set are linearly separable from each other. Okay. So our goal is to create a face classifier that can extract feature vectors from face images. And these classifiers consist of two parts, which are the feature extractor and the classification layer. So your model needs to be able to learn facial features like skin tone, hair color, nose size, etc., from an image of a person's face, and then represent all of these as a fixed length feature vector called a feature embedding or a face embedding. So in order to do this, you guys are going to explore architectures consisting of multiple convolutional layers. And by stacking these different convolutional layers, we essentially are able to get a hierarchical decomposition of the input image. For example, our first layer can extract low-level features, and then the second layer may extract combinations of these low-level features, which obviously allow for our network to learn better. And then the final feature vector that we obtain at the end is going to be passed through a linear layer, followed by a softmax to classify it amongst n categories. Then you can use cross-entropy loss for optimization. And then the feature vectors are also going to be used for the verification task, which we will be talking about in the next recitation. Yeah, so now we're going to be talking about the data set. If you guys have read the write-up, you know that this is a subset of the VGG phase 2 data set. This data set is very commonly used in research and industry, and these images are essentially downloaded from Google Images, and they have a large variation in factors such as pose, ethnicity, profession, etc. And so we have a large number of identities and image per identities in this data set, which allows us to cover a large range of poses, ages, ethnicities, all the different categories mentioned. As you guys know, we have 7,000 different identities, and the data set has also been class balanced, which means that each class has an equal number of training images. And so for classification, all you have to do is learn to classify an image with the correct face from 7,000 different identities. And once again, this is also in the write-up. Implementing the dataset and data loader class for this homework is actually extremely straightforward. We're just going to be using the image folder class from the Torch Vision library that you can import in, and we're just going to pass the path to our training and validation set into that. And so the image folder class is going to automatically be able to infer labels and make a dataset object from the path that it's passed in, as the folder names correspond to the classes, and the images of different respective classes are placed in folders with the same names. So the only thing that you guys really need to remember is to pass the image transforms into the dataset class when you're doing data augmentation, which is very important, and it's good to implement if you want to get high accuracy. So before we dive into the actual implementation, we're going to think about how exactly do we want to differentiate faces. So yeah, your answers are going to contain skin tone, eye shapes, etc., as we talked before. And so intuitively, facial features vary extensively across people. So our main task is to create a model that produces good face embeddings, which means making use of the features that can be used to discriminate between images from different classes. And so these extracted features are going to be represented in fixed length vectors. And once your model can encode these discriminative facial features into embeddings, you're going to pass it to a fully connected layer to generate the corresponding ID of the given face. So yeah, this is again what we've talked about before. Your input is going to be several images. You're going to have different convolutional layers for feature extraction. You're going to get the face embedding, pass it through the classification layer or the linear layer, and then we're going to pass that into a softmax, which is going to essentially normalize the vector that we got from our linear layer to classify the image amongst the n different classes, after which we're going to use cross-entropy loss to optimize your network, to learn the weights better, to predict the correct person for every training image. And then we can use a validation set for fine-tuning our model, which we have provided for you. So one important thing to remember is that having a network that is good at feature extraction or a network that's able to efficiently train is the core of our classification tasks. So this particular homework requires you to train very deep neural networks. And as it turns out, deep neural networks are difficult to train because they suffer from vanishing and exploding gradients type of problem, mainly because information from shallower layers sort of struggle to propagate to deeper layers within the network, the deeper our neural network actually gets. So we're going to learn about skip connections, which essentially allow us to take the activations of one layer, a shallower layer, and feed it into another layer, which is much deeper in the network, as you guys can see in the picture over there. So using this logic, we can build residual networks or ResNets, which enable us to train very deep neural networks, sometimes even networks of over 100 layers. And so if you guys see the picture over there, we essentially take the output of a shallower layer and just feed it into the output of a deeper layer within the network. And this is essentially an identity mapping. So there are no like specific parameters that we need to learn in order to actually implement this. And this allows deeper networks to be built and trained efficiently. And popular architectures that make use of residual blocks are MobileNet, ResNet, ConvNext, et cetera. Please read these research papers as you will be required to implement these from scratch. And we're now going to be going over the starter notebook. So,
So
Go ahead.
is there any number to the number of layers for which the identity should be applied?
So this, no, there's no fixed number that I can give you now, but I think you would have to read the different research papers, and because different neural networks are going to implement them differently. So yeah, you're going to have to read the research papers for those. But yeah, we're now going to quickly go over the starter notebook. So if you guys have that, you can pull that out. And then these are obviously the different points that we're going to hit, the different sections within the notebook that you're going to have to fill out. So I'm going to hand it over to Paul.
Okay, thanks. Let me share my screen. Okay, can you guys see my screen? My screen visible?
So do you guys mind joining the Zoom from your laptop so you can see the starter notebook? If that's possible? Just while I pull it up.
Okay, it's fine. So for the homework 2 part 2, we'll be doing 2 tasks as we have seen, the face classification and verification. And as we all know, this homework has no limit to parameters, like unlike the homework 1 part 1, which will tell you that you can use assembles, different networks which are forming weak learners from different networks and making a more stronger network. And also, you should watch out for some things in the homework 2 part 2, like because of the amount of GPU and all, you should always try to use this we basically have this error more frequently, put out of memory, and then what you can do is to reduce your batch size and empty your cache. Yeah, so basically I'll just run you through the other sections of the notebook. Most of the functions have already been implemented because we want you to focus on building the architectures. You have to read papers on different CNN architectures and try to implement that and see what works. So this is just importing your libraries and dependencies. If you're using Google Drive, then you also need to set up your drive, because this homework is
everyone
going
able
to
to see
this
the
train.
notebook? Oh, okay, good. All right. Go ahead, Paul.
Okay, so since you're going to be training for a very long time, so it's important for you to always save your models so that you don't do work in vain. So here you just need to set up your cargo. You can copy the code from the homework 1 part. Homework 1 part 2 is basically the same code. Just copy and change a few things, and then you can run that to set up the cargo, and then download your data sets. Then this is your configuration. So you basically put all your configurations here, because you want to be able to log this to your 1DB and be able to also see where you need to tune. So basically 10 epochs is recommended for the early submission. So if you can implement the architecture recommended for the low cutoff with 10 epochs, we believe you will pass the low cutoff, the early low cutoff. So one thing you should know is that for meeting the medium cutoff and the high cutoff, you need to train longer and you need to use more extensive architectures. So your classification data sets, these are basically just setting up your data sets. You have your directories, which you would have downloaded from Kaggle. Then you have the transforms. Transforms with Touch Vision help you to augment your data. So you can implement different kind of transforms. You have the horizontal flip, the vertical flip, but we will not advise to use vertical flip. But then you should just read more on different data augmentation. There are papers that have compared image classification and the augmentations that work best. Some augmentation will make your performance, will not make your performance increase. Some of them will just negatively affect your performance. So you should definitely choose the augmentations you want to use, right? And here you load your data set, right? So the image folder is a module in PyTorch that helps load your data. Since basically your images are in folders with their names and then they have their labels. So this will quickly help you load your images. You can load your train data set and your validation data set. So these are creating data loaders with the batch sizes you have set, and this also your validation, your loading your validation data set. So for the test data set, you require to do something similar to what you've done in homework 1, part 2. Create like a data set class where you load the data set. And this is because image folder cannot help you this because of the test data set have no labels. So basically you have to manually load this, but then we have implemented most of these functions and we want to just focus on the architectures. But it's good that you understand how this works as well, so that you can know how to debug your code, basically. So I think one thing I skipped is we don't usually do augmentations for validation data sets because basically it's not like a good practice. But I know that some people do it for their test data set, and I think is a technique. But basically for this assignment, I don't think you need to do that. Just the augmentation is okay with in the train data set. Yeah, so this is just printing out the describing data and the characteristics of data. So we have 7,000 classes, and the number of your training image is 14,000. So you see that when you compare this, you see that it's basically 20 images per class, which is very small because you are training like a very deep neural network. So you will basically need to do some augmentation to add more data sets, right? So that your models can really learn the important features in your images. So it's also very good for you to visualize your data once you have loaded them in. So this function here, you don't really need to know the intricacies of this function. It just basically helps you to print out the pictures which you have loaded in your trained data. Yeah, so for the early submission, you just need to implement a very shallow and simple network, CNN actually. So here you just need to implement a 4-layer convolutional neural network, and the channels have been provided to you, and different stride and the kernel width you will use for each convolution. And also remember that you need to pad. And why do you need to pad is because when you are convolving, depending on the kernel size and the stride, your output or your spatial the output dimensions of your output channel, they tend to decrease. So you need to pad them so that if you want to retain the size of your output. Yeah, so you need to fill out this architecture. So yeah, so like fill out the self.backbone, which is just a simple architecture for low cutoff, and then pass that to a linear layer. Remember the self.backbone will just do the feature extraction because we already see that CNN is just for feature extracting, and then after extracting features, then those features are embedded. So those are really important features which are now projected by the linear layer, right? So the cell.cls is basically will be a linear layer projecting those feature embeddings, right? Or fit embeddings. Here, I'll just talk about return fit. So when you're doing verification, which we're not discussing now, but when you're doing verification, it might be important for you to use the feature embeddings rather than the output as the softmax, the probability. So you want to use the feature embeddings to train like contrastive loss. We'll look at contrastive loss later in the next recitation. But now, for now, you just need to use your output from your linear layer to do the classification. But if you want to use the feature embeddings, then that will be your fits here, right? So basically, you just set up your network and then do the forward and then you return the out, right, for your classification. So they set up everything. These are just like your parameters. You define the loss function you want to use, your criterion, and that's your cross entropy. Then the optimizer. We also encourage you using some scheduler, so you can try out these different schedulers. And also, if you have like GPUs C4V100, you can also use mixed precision, right? And the mixed precision helps to speed up your training time since you're using both flow 16 and 32. Yeah. So yeah, so we have the training function already set up for you. You don't really need to worry about this, but just understand the structure and how it works. Because future assignments will require you to implement those by yourselves. And also we have the validation function already set up for you. Basically that's it. So 1 dB, we already know this from homework 1, right? And then this is your experiment. So this runs your epochs. So basically in 10 epochs with the shallow network, with the network we predefined for you, you should be able to cross the low cutoff. And one thing you have to know is that most of the architectures you will be implementing in these assignments will require you to read papers and be able to implement those papers. So we encourage you to start early and start on time so that you are able to, get your model running and training, right? Yeah. So any questions?
Yeah, so I think we've covered pretty much everything for today's recitation. So you guys are, I think, yeah, you guys are free to leave. If you have any questions, you can stay behind, ask me. And don't forget, there's a bootcamp tomorrow. So if you want to get an early start on homework 2 part 2, make sure to attend that. But yeah, thank you guys.